Last time we have learned several important characteristics in Fourier transform. One of them is duality. Duality means that for example, in this example, if you have pulse in time domain, when you do the transform, there will be a zinc function in frequency domain and vice versa. Therefore, you will have, in case of if you have rectangular in frequency domain, there will be zinc function in time domain. Of course, the form is slightly different, as you can see in here and here. However, this duality is often observed when you do the transformation from time domain and frequency domain. Also, not only duality, we learned that it has several differences. For example, if you make the signal in frequency domain to be shrink down, in time domain, they will be spread out. So the direction of trend is slightly different in time and frequency. Also, we have learned a few characteristics. Say, if you know in page 8, if you know your Fourier transform already, x, j, omega, if you already know your Fourier transform, you can find out Fourier series coefficient right away by considering that this is sampling, taking samples at a period of W0 in frequency domain. In the other way, if you know Fourier series, in page 14, if you know the Fourier series coefficient AK, you can find out your Fourier transform basing on this equation, which is considered as an impulse train in frequency domain. So there is an impulse at a spacing of omega 0, similar to getting a sample, having an amplitude of 2 pi AK. So if you know your AK, your Fourier series coefficient, then what you do is you first find out what is omega 0. Omega 0 is 2 pi divided by the period. So from that you can find omega 0, and then if you already know your AK, Fourier series coefficient, the amplitude of each frequency is 2 pi AK. So you can find out Fourier transform in that way also, other than solving those integration equation. So keep in mind, we have learned that Fourier transform is both for periodic and non-periodic signal, duality in time and frequency. However, they're slightly different, like spreading out, shrinking in. And finally, we have two equations going from Fourier transform to Fourier series, and vice versa, Fourier series to Fourier transform. In these two equations, is only valid for periodic function, because Fourier series is only valid for periodic function. Fourier transform does not. Fourier series is only valid. Therefore, this one is only valid for periodic function. And then we have solved several simple problems. Hello. And began to learn the properties. So we have learned there is a linearity, time shifting, which is given as if they shift by 0, they will come as e minus j omega t0 in here. For conjugate, they typically have the conjugate of x will be given as x large X star minus j omega. However, if x is real, then omega is conjugate symmetry, which meaning that x j omega, which is here, equals x star minus j omega. So if you switch minus, does not matter. So you can represent in the way like this. If x is real and even, then this is the original one, aj omega. Because if x is real and odd, xj omega will be purely imaginary and odd. Those are the property which is very similar to Fourier series. Differentiation and integration may be the most common thing you have observed by far. So when you have a Fourier transform already, is differentiation, which is like this, they will be j omega times xj omega. In integration, there will be 1 divided by j omega plus some initial values. But in most cases, we have learned by far, we did not consider those initial values because we have assumption that that initial value is 0. However, if the initial values are not 0, consider the second term. So this one is quite similar to what you can see, like if you have resistor, inductor, for example, how we do it. You have, okay, this is our R, this is our j omega L or SL sometimes. That's what you already have it. Because in this equation, if you have current, if you have a voltage, the total voltage from here to here, total voltage from here to here will be voltage in here, which is Ri, plus L di dt. That's what you can see in here. So this is time domain. This is time domain. Then you already learned how to change to frequency domain, which means omega. So you can now this V is T actually. This Ti is also T. However, when you change it, you probably remember that this one changed to capital, and they have j omega or sometimes S, which is given as R plus j omega L and large capital j omega, or R plus SL times IS. So this, and then you calculate that, okay, our transfer, our impedance is what? V divided by I, which is R plus j omega L. This is our impedance. So you already calculate the process in basic circuits, even in mechanical system. In mechanical system, is it too fast? No? I assume that you already know this. In case of mechanical system, if you have, all right, I have my spring and then spring and the mass, and try to give a force. The force will be given as sometimes looks x 2 times differential plus kx, something like this. This is time domain signal, both f and this is time domain signal. And how you calculate this response, you automatically learn that you do the frequency domain response, which is given as omega likewise, and this f is actually time domain signal, but they change to frequency domain signal. I think you are more familiar with S, right? And then you change that, okay, m 2 times differential, so s square x s plus k x, meaning that m s square plus k times x s. So your response will be f divided by x, which is looks like this. So you already have used this one in electrical engineering, also mechanical engineering. So if you see this, I think I emphasized this one in the beginning of the lecture. So this j omega means Fourier transform, which we are learning. And this S is Laplace transform, which we will learn in chapter 9, I think. So once again, this S is complex number. S is complex number. So it can have real term and imaginary term. In case of j omega, they does not have real term. They are purely imaginary. right? So that's the major difference. So in case of S, they have real term, which I explained that they covers in real imaginary axis. They basically covers all the complex domain. In case of J omega, they does not. They combine two unit circle. So that's the reason they are major difference. So you can consider that Fourier transform may be a subset of Laplace transform. There is an image like that. However, surprisingly enough, in that case, typically what happens in scientific world is Fourier first invented Laplace transform, and then like 20 years later, Laplace invented Laplace transform later. So typically in many scientific findings, one guy sounds very strong voice. So one guy developed, one guy developed a new finding. The next guy, after like 10 or 20 years later, having more deeper understanding, that's kind of evaluation of scientific process. But surprisingly enough, this Fourier and Laplace are almost live in the same age. They only have, I think they died only 10-year difference, very similar age, and they lived in Napoleon age. So if I can have a time, I will explain the relationship. However, surprisingly enough, these two guys lived in the same age. But this one is a little bit smaller scope compared to this. However, when you learn the Laplace transform, we will emphasize the convergence, meaning that the value may not exist in many cases. Anyway, in short, I say that differential and integration may be very popular thing you're already seeing in many engineering world, like this electrical system or mechanical system, because you already learn it. So keep in mind, but in here, if you have a capacitor, for example, if you have a capacitor, you add it, okay, here is a capacitor, capacitor integration IT, right? And then they will be changed to, okay, J omega over like this, right? Without initial values. So this one comes from our integration, which is J omega over 1 divided by J omega plus initial values. But we assume that this one starting from zero condition, there's no initial value. Therefore, we ignore the later part. So we just automatically have, okay, J omega C over 1 is our impedance. However, actually, for integration, if you have initial value, you have to consider this one. And time and frequency scaling, we have xt, will be xat, which is a scaling time. They will change to 1 over a and 1 over a in frequency domain also. So if you have a scale in time or frequency, actually what this one shows here is when x is 80, they will be looks like that. But it can be worked as reverse way. If you have, say, all right, I have j omega divided by a, they will, when you do the reverse Fourier transform going to the time domain, they will be a times x80. They will look like that. So you can go here, you can go here, two ways. So we have skimmed through several properties, which is important to understand in Fourier series, Fourier transform. The other one, property number 6 is duality. Duality means like a rough idea that Fourier transform going from time to frequency and reverse Fourier transform going from frequency to time have not the same but similar form, which is we have seen in the rectangular function and zinc function relationship. So, for example, in here, this is the example we already covered, those two examples right here, these two examples. I write them in here so that when this is a rectangular signal in time domain, they change to zinc function in frequency domain. Rectangular signal in frequency domain, they change to zinc function in time domain. So they are very similar, but not the same. Please note that, because in here there's the omega, here's the pi t, which is different. So the form looks similar but not exactly the same. So keep in mind on that. However, they have similar trend, I will say. That's what I'm saying. Another example is that if you can, we will learn about that in later this table. If we just learn that dxt dt, when you do the differentiation, their Fourier transform will be x j omega, right? If you have differentiation in frequency domain, which is shown in the example, what happens? There will be minus j t x t, which is quite similar, right? They're quite similar. So of course, not the same. I'm not saying they're the same because it's plus and minus, so slightly different. However, you can look at the trend. They're quite similar. What about one more example? We just learned that shift in time, if you do that, they will be probably minus, right? Right. Minus j omega 0, I'm sorry, minus j omega t 0 times e j omega. That's a typical way you are going from here to here. What if you shift in frequency? If shift in frequency, then you will have e j omega 0 t x t. So again, very similar. However, the polarity is different. So if you see those three examples, zinc function and rectangular function relationship, differentiation relationship, also time shifting relationship, you will see from time to frequency and frequency to time, they are quite similar, but not exactly the same. This property is called duality. They say go both direction. Okay, questions by far? All right. So once again, we will have Parseval's relationship. So we have Parseval's relationship. Do you remember the Parseval's relationship in Fourier series? They have similar things. So if you have in this side will be quite similar to your Fourier series. Let's take a look at our Fourier series case. So keep in mind, they're sometimes quite confusing, but sometimes always make sense. So Parseval's relationship, this is for the discrete time. So let's have continuous time case. So in Fourier series, we have average of original signal, absolute value square, which is basically power, is equal to sum, right, of a kind of amplitude of each frequency. This is Fourier series case, possible equation in Fourier series case. What about our case? Our case is in Fourier transform. Continuous time Fourier transform, it looks like, equals to, should be x j omega square e omega, I think from minus infinite to infinite, right, to pi over 1. So how we derive is quite straightforward, because as you can see in the derivation, this absolute value, you will have x times s conjugate, right? Right? And then you change this x star to this, because we already know how the conjugate works. And then if you follow the trend, then you will find out what is, and this one eventually change to like this, because as you can see in here, you can see that x star is here, and this xt and e minus j omega t will change to x j omega. X j omega times x star j omega will be absolute value of x squared, and 2 pi is still valid, so pi will come out. But let's think about what's the meaning of this equation. Of course, derivation is very important. But why this one we are learning this? The claim is still the same. We claim that in possible relation of Fourier series, we say these two are basically same function, same signal. We calculate the power of x, the absolute value square of power, this one, from the original signal, or adding each frequency signal's amplitude power, I would say. So this one is whole signal, this one is sum of each component. They should be same. That's the meaning of possible relationship. This is the same one, because now this one we compare two signals which are the same. Both of them are time domain. In here, we are comparing two signals which are the same, but one is in time domain, the other one is frequency domain. So what you do here is this xt and this xj omega are actually the same signal, right? We change this one to frequency, change this one frequency to time. They should be the same signal. However, they plug it in two different domains. One is time, one is frequency. So they should be the same. That's the meaning of this equation. So now this is another interesting and important characteristic in system analysis. A long time ago, in chapter 2, I think, when you learn about the series combination, we have learned that, okay, here is a system response H1, system response H2. To calculate that, we have to do a convolution. What is H covering this whole thing? There will be HT convolution H2T. We have calculated in the way. So convolution requires a lot of effort to find it. But I gave you a little bit taste about using frequency domain. You can change this one to corresponding H in frequency domain, and the system response covering all of the signal, all of the component will be H equals H1 multiplication of H2, which saves a lot of your effort. And then you go back to time domain. I once explained about the process. So this is it. So this is possible. So in this characteristic for convolution, say H and X convolution, which is output of, they will be same to Y J omega. Of course, and then H J omega times X J omega. So what you can see in here is in time domain, for system analysis, if you have a series of systems which is often observed in many engineering, we have to do the convolution to pass through each of them. If one system say H, to find out Y, you put X to the convolution, find out Y. You know, remember that we have like some impulse convolution of this signal, and we reverse it, shifting from lowercase case, uppercase, see where it's overlapping to find the convolution. That's convolution. That's one way. I'm not saying that this is wrong. We can do that. However, for calculation-wise, if you can find out each system and input, or even different system, and just multiply it, that saves a lot of effort actually. So this equation is another very important characteristic why we have to learn Fourier transform. So let's learn about the cases. So this is a case. We have learned that to find out the whole system, we have to do the convolution, which is shown in the graph. However, if you change it to frequency domain, then will be equal to multiplication of each. Of course, they can be reversed like that. So this is very simple property. However, very helpful to analyze your system, because definitely multiplication is much easier compared to convolution. Definitely, right? It saves a lot of effort. That's the reason that every time you learn the circuit, every time you learn about the system, you always have, okay, here's Y, and we have something times X, and say, okay, X over Y is H, which is some symbol, right? We always try to find the H, because H is what? Representation of the system. How we do response, we give an impulse. We give an impulse as an input, then system itself will come output. That's how we check the system. And this one, H, is system itself. You can find it. But to find it, this one is way more, requires much effort to find it. So what if you just change the frequency and calculate over in frequency? What about? And in later chapter, we have, this one is continuous time Fourier transform. Have you seen Xn in this chapter? No, right? We haven't learned it. So this chapter is only for xt. So in previous chapter 3, Fourier series, we have both xt and discrete time signal, both of them. In this chapter 4, is continuous time Fourier transform. Only talk about continuous time case. And in later chapter, next chapter is called discrete time Fourier transform, CTFT. They talk about this. There are some special thing over there, slightly different. So, and then later chapter, 2 chapters later, we will have time and frequency analysis, which, what if we just change the frequency and then analyze in frequency instead going back to time? Now, how we can analyze the in frequency is what we learn in chapter 6 or 7, I think. Okay? So this one, I put the slide so that you can take a look at, so then how we can derive, how we can verify this relationship. So let's do a little bit math. So say convolution. Convolution is what? From minus infinite to infinite, h tau x t minus tau d tau. That's convolution, right? Of course, you can switch x and h. So let's follow the derivation so that you can have x, you can have h. To find y, let's find y, which is, if you see this large f, that means Fourier transform. Sometimes you will see, I'm sorry, this looks like very beautifully looking L, that's Laplace transform. So this f, sometimes people put f like that, but this f has many meanings, force and many things. So for distinguish purpose, we put a beautiful f representing this is Fourier transform. So there will be Fourier transform of y, which is Fourier transform of that. So if you put Fourier transform y, Fourier transform is what? From minus infinity to infinite, yt exponential minus j omega t dt. If you put them instead of yt, they will look like minus infinite to infinite x tau h t minus tau d tau. That's what you see in here. Remember, even though they are both from minus infinite to infinite, this one is paired with this. This one is paired with dt. Of course, you can switch. Doesn't matter. If tau is inside, t is outside. If tau is outside, t is inside. Doesn't matter. Anyway, we have to calculate. So let's switch a little bit. What I'm saying here is tau is inside, t is outside as a variable. But if you have t is inside, tau is outside. Let's find out. See how things are different. So this red now go to here. This yellow, they go to here. Right? So we just switched order. And how we can find it? For things related with t, the things related with t should stay in here, right? X tau does not have any relation with t, so we can take them out. X tau can take out. ht should stay in here. And e minus j omega t also should stay here. And then using the time scale property, let's take a look at, let me rewrite this one more time so we can see more detail. So this is just reversed the order of integration. And you can see in here. Inside here, they are exactly the same to Fourier transform actually. Fourier transform of this, right? Fourier transform is what? Minus infinite to infinite function e minus j omega t dt. That's a Fourier transform. So this one, the thing inside this one, they consider to be a Fourier transform of h t minus tau. And t is our variable now. So tau, we can consider them as a constant, which is time shifting. Remember, time shifting of x, they change to e minus j omega t 0, right? So if you do that, this one change to h j omega times E minus J omega tau. Right? Now here is tau corresponding to T0 because our variable is T. Can you question? Anybody have what? Need one more? Okay. So until here, from here to here, questions. Does it make sense? So one more explanation about this. If you see this form, the thing inside here, Fourier transform, where we have this is Fourier transform, right? If you compare this and this, the thing inside this bracket, minus infinity to infinity is the same. This is a function we want to do the Fourier transform. E minus j omega is over there, dt is t. So now the function we want to Fourier transform is h t minus tau. This is function we want to do the Fourier transform. And t minus tau is what? T is our variable here. Tau is considered to be a constant in this bracket because this is not a variable in this bracket. So they can be considered same to here. T is here. Tau is T0 corresponding to T0, which is constant. When you do the Fourier transform, this one will change to ej omega T0 times xj omega, which is we have learned in second property. So this can be considered that, okay, h times ej omega instead of T0 tau. So that you can switch this whole bracket to this. So they will change to, all right, h j omega e minus j omega tau. And then in here, h j omega, now the variable here is tau. H j omega does not have any relation with the tau. So we can take them out. We can take them outside. Right? And then what happens? Minus infinite, infinite, x, now tau, e minus j omega tau, d tau. So what is this? X j omega. So in short, y becomes h times x in frequent domain. You can, if you want to review it, this slide contains all the contents except explanation. So you can revisit. So in short, this is the very typical in short, this one is valid, which is a very strong property we can use. Question? No? All right. Finally, multiplication. So this one is also part of duality. Duality is what? From frequency to time, time to frequency, they are similar but not the same. So in here, the convolution changed to multiplication. What if you have multiplication instead of convolution? Then we can imagine, okay, they somehow changed to convolution. Right? They somehow changed to convolution. Actually, that's true. There looks like 2 pi over 1 convolution of h and s, which is given as 2 pi over 1 from minus infinite to infinite, h, say h, j theta, new variable instead of tau, x, j, omega minus theta. So in convolution, remember, we have minus infinite to infinite, x, tau, h, t minus tau, d tau. That's convolution, right? In here. So in frequent domain, tau corresponds to j is theta over here. Range is the same, and the function is t over here. and minus tau. So form is quite similar except this one. So still duality. So from here to here, they change the convolution. From those convolution to here, there were 2 pi times multiplication. That will happen like that. So the duality is still valid in this case. So you can find out that, okay, you have multiplication in time domain, it's better to do it, right? If you have convolution in time domain, you better change to frequency. But sometimes you have to calculate in frequency because this one is very often observed in communication system. In communication system, called frequency. Try to shift the frequency. To shift the frequency, what is the simplest way? If you have some signal, say 2 pi times 10 kilohertz t, you have this system. If you want to shift the frequency, what's the simplest way? You just multiply by other sign. Okay, I have 2 pi 10k hertz times t. If you do multiplication by sine, right? This one becomes 0 to 220k. So you can change the frequency very easily by multiplication, which is very, very often observed in communication systems. So unfortunately, in those systems, you have to do the calculation, and to see the frequency response, you have to do those things, unfortunately. But keep in mind, duality is still valid in this case. So you can see that it's typical form of modulation. Modulation means change the frequency, massage the frequency kind of things. So before we finish, let's do some problems. So now we learned many properties. So you can have better understanding what's going on, hopefully. So what I'm showing now here is several examples you can utilize. But this is not a solid answer. You can do other method if you prefer. So in here, let's find output signal. This is example 4.19 in your textbook. Say that our system response is E minus AT UT. And our input to the system is X E minus BT UT. So let's find the output. What is the output? So what is the output? So first of all, the thing we have learned by far is using the convolution, right? So okay, let's do this. And E minus AT is decaying, right? And they are valid after 1. So there's nothing here, this is only valid in here. Yes, this is response. Likewise, in the input, they will look like this. Of course, the slope is different. E minus BT now. So to the convolution, what you do, we have X tau, let's change this one to tau, times H T minus tau. So when this one changed to tau, this is our X, this is our H T minus tau. And this is tau. How we do it? We reverse it, right? We reverse it. Here is our T. And then let's start from the lowest case, nothing overlaps. Now from here we begin to overlap. And let's calculate the overlapping area from 0 to t. So from here to here, 0 to t, we calculate, I don't know, E minus B tau times H, E minus A T minus tau, B tau, and calculate. This is doing the convolution, right? So you can do that. There's nothing wrong. But the other way you can do it here is, let's use some new tool we have learned. So let's calculate this one's Fourier transform. So Fourier transform, this one is what? Minus infinite to infinite, e minus at ut e minus j omega t dt. This is definition of Fourier transform, right? And then how we do it? Okay, this one is to remove this. This is only valid from 0 to infinite. Other than they are 0. So let's change this one to 0 to like that, right? From 0 to infinite they are 1, until 0 they are 0, right? So what's the integration of this? E minus a plus j omega t dt. What's the integration of this? There will be, alright, minus a plus j omega over 1, which comes it, and times e minus a plus j omega t from 0 to infinite. Okay, and then in here we assume that a is larger than 0. This is something very important property because we have not covered convolution yet, convergence yet. We have decree condition in the slide in chapter 3, decree condition in this chapter also, but I will come back when we need it. As a is larger than 0, if you put infinite, they converge, they go to 0. If you put 0, this is 1, so they will have something like this. Something is wrong. So if you put the slide in the 28, this one is a table 4.1, which is property of Fourier transform, which we have learned by far. In next table 4.2, they give you an idea that what is typical examples you can see in Fourier transform. So our case is over here. E minus at ut, they will be, looks like this. So let's see, where is wrong? So by far this is right, however we are so after calculation, this one e something minus infinite, right? Minus e0. So minus infinite, this one becomes 0, right? And minus by minus is what? Minus is plus. E0 is what? 1. So this is our calculation, which you can see over here. E minus at actually equals a plus j omega. So this is what you can see in here. Using this property, so this one's Fourier transform is what? H j omega equals a plus j omega 1. What about x? There will be b plus j omega over 1. So output is what? Multiplication of these two. So you can see that. Alright, the output is a times x, which is a plus j omega, b plus j omega multiplication over 1. This is your signal. So this is your y, your output. You can write this one like this, but many solutions you probably need an answer that what will be time domain signal. Because in convolution, our result is time domain signal. This one is frequency domain signal. So some question ask you that what about the time domain signal? So let's use reverse reverse Fourier transform. So we have learned that this one's Fourier transform will be A times J omega. We derived it. So let's calculate this one a little bit. This one is multiplication. So let's divide them. Say, okay, can we do that? Let's calculate if you can do that. Yeah, we can do that. Except that we have, oh yeah, this is A, this is B, and A, large A times B plus large B times A equals 1, right? And A J omega times A plus B equals what? They should be 0. Right? So in here, all right, A is minus B. Let's put it over here. Minus B plus A times B equals 1. So if you put them in here, you can divide them. You can divide them like that. So should be B minus over 1, I think. 1 minus 1. That's what you can see in the last equation. Any questions before? Questions? So what you do, we know this, right? So the reverse of this one should be this. So that's what? Reverse of this one is what? E minus AT UT. Reverse of this one is what? Minus, because it's minus, U E minus PT UT times this. This is your system response. So much faster than convolution, right? So instead of using convolution, we change the Fourier transform, calculate in Fourier domain, change the form to be easily reconvertible to time domain, take the time domain signal. This is another way you can do it. Of course, I'm not saying that convolution is wrong. Convolution is right. But do something easier, then you do it. Let's put another example. Let's skip this. This one is the example 4.16, so get quite similar to what we've done before. This one is interesting, actually. This one is interesting. So this one is what you often observe in telecommunication systems. So say that, all right, we have, this is frequency domain. Both of them is now frequency domain. In frequency domain, let's say our S and P is our signal. We want to have frequency domain spectrum, frequency domain signal of multiplication of this S and P. And S, we don't know what's S, T. We know that S, J, omega in frequency domain, they looks like, sometimes looks like snowman, right? And we know that P is cosine omega 0 T. In this case, what will be the frequency spectrum of R, which is multiplication of S and P? This question. In short, we want to have multiplications frequency domain spectrum. We want to have frequency domain spectrum. And we know that P in time domain. We don't know S in time domain, but we know S, J, omega in frequency domain. That's the question. So first thing you can do over here is you can either find this envelope, change to time, do the multiplication. That's the first thing you can do. However, this one looks like that's not so easy to do that. So what if we do, and anyway, we have to go back to frequency domain, because the question is, what's the frequency spectrum? Therefore, okay, let's do that in the frequency domain. So we have this domain. This one looks like the same. And we have in cosine omega 0 t. We already learned about this, what the frequency spectrum, because if you remember 2 pi ak, this is periodic signal. So you can have Fourier series coefficient. So we have learned that, okay, let's use this. And this one is has a plus omega 0 and minus omega 0 their value, which is case 1. And we know this, right? So we already calculate that in frequency domain, that looks like at omega 0 and minus omega 0, they have some value, which should be pi divided by something, right? So we already know the response. Also, you can calculate in Fourier transform, say from minus infinite cosine omega 0 t exponential minus j omega t dt. How we do it? This one, they will change to 2 over e j omega 0 t plus e minus j omega 0 t. And divide them and do the following thing, you will find the same answer. Doesn't matter. So, in short, we already know you can calculate from Fourier transform 2 ways, using the Fourier series coefficient or do the Fourier transform right away. With frequency domain, we know that there will be omega 0 and minus omega 0. So like that. And then what? We have learned that in multiplication in time, there will be the cycle convolution. So it will be 2 pi over 1 s j theta p j omega minus theta d theta. That's our answer. So let's do the convolution here. So this is S, this is P. So let's shift these two lines. Say this, my two finger is two lines, omega 0 minus omega 0. Let's shift them. Let's reverse them first. Even though they reverse, they were the same polarity. They're symmetric. And then shift to the bottom, skim to here. From here, they begin to overlap, following the shape, because this is 1. This is not exactly 1. They have some value, but this is constant value, right? So until here, they follows. And then after passing this one comes in, they begin to follow. Remember that in here, your assumption here is that we have omega 1, omega 1. Omega 0 is larger than omega 1. So when this one is here, until they pass, the second one over here does not catch this side. So it's like a scanning this one. So what you do here is reverse. However, even though reverse, they were the same because they're symmetric in y-axis. Starting from scanning, and they begin to scan this. So the shape comes in, but the scale is different, scale change. And then after passing this, the second one comes in, begin to scan it, and show this. So if you plot that from here, which means the theta becomes omega 1, then this one became, the value will come out. So that looks like two signals having spacing of omega 1, omega 1, omega 1. And the amplitude slightly changed because of this amplitude and this one. So you can see that. So by far, in table 4.1, they summarize what we have learned. So in here, you can see that this is may not periodic signal, may be periodic signal, both cases. Linearity, time shifting, frequency shifting, conjugate, time and frequency scaling, convolution, multiplication, differentiation, integration, even differentiation in frequency, we have learned that, and also several conjugate cases and Passavant's equation, which is a summary of Fourier transform property. Different from chapter 3, this one has one more table in summarizing several general Fourier transform you will see. So several example will be like that. This content is not so good, so please take a look at your textbook. However, if this one talk about the exponential, something like omega t, this is very popular, right? This transformation will be delta function, shifting in frequency. That's what they say in this line. Line, which we just learned, cosine omega 0 t. So keep in mind that this side is time, this side is frequency. So the variable at left side in your side is t. Variable in right side is omega. So keep in mind. So this one, they change to delta omega minus omega 0 plus delta omega plus omega 0. Meaning that now omega is our variable. Omega is our variable. Therefore, there are two signals having different amplitude at omega 0 and minus omega 0. Likewise, in sine, they have omega 0 and minus omega 0. The amplitude is slightly different. Rectangular square, if we'll see that this is used to be rectangular signal will change to sinc function. One periodic signal, if this is periodic signal, this is non-periodic signal, they are still sinc function. Likewise, the delta function, the rectangular function in frequent domain, they change to sinc function in time. Delta in time domain, they change to 1 actually. This is a very important property. If you have unit function, what happens? Well, unit function, there can be integration of delta, right? Integration was what? J omega over 1 plus values. And in here, E minus AT, UT, we just derive that they will change to A J omega over 1. If we have T E minus AT, we have T in front, there will be looks like this over here. So of course this is a lot of things are complicated, but many of things we already learned during the lecture. So these two tables will be a good reference you can utilize.